The scratch that cuts glass, stress concentration, and fracture. A sheet of glass lies flat on a workbench. A worker does not saw through it. Instead, a small cutting wheel draws one quiet line across the surface. Then the glass is lifted and bent. Suddenly, it separates along that line with a clean, sharp edge. The strange part is that the scratch seems too shallow to matter. How can a thin mark control the breaking of an entire sheet? Glass is strong in some ways, but it is also brittle. In a ductile material, such as many metals, atoms can shift and deform before the material fails. A metal plate may bend, stretch, or dent. Glass does not have that freedom. When local stress becomes too high, it tends to crack instead of flowing. The key is not only how much force is applied, but where that force becomes concentrated. A scratch on glass is not just a mark. It is a tiny crack with an extremely sharp tip. When the glass is bent, tension develops near the surface. Around the sharp tip of the scratch, the stress becomes concentrated into a very small region. The sharper the cracked tip, the stronger the concentration. Once the stress at that point exceeds the material's resistance to crack growth, the crack begins to move. After it starts, the crack naturally follows the weakened path. The original score line guides it, so the break can be straight and controlled instead of random. This is why glass cutters use a hard wheel or diamond point to score the surface before snapping the sheet. Ceramic tiles can be cut by a similar method because ceramics are also brittle materials. A common misconception is that the tool cuts all the way through the glass. In ordinary glass cutting, it usually does not. The tool prepares a fracture path. The final separation happens when bending or pressure drives the crack through the thickness of the glass. Fracture mechanics studies this process in a more general way. Engineers care about small cracks because a structure can fail long before the whole material is uniformly weak. A tiny defect in an aircraft window, a bridge component, a ship hull, or a pressure vessel can become dangerous if repeated loads make it grow. That is why inspections often search for cracks too small to notice casually. The same principle appears in everyday packaging. A small notch at the edge of a plastic bag makes it easier to tear open. The notch concentrates stress and gives the tear a place to begin. Without that notch, the same material may be surprisingly hard to rip. A line scratched into glass is not a cut in the ordinary sense. It is an invitation to fracture. Force finds the weakest path, and a tiny crack tells the whole sheet where to break.